Ever needed to debug a server-side function, but couldn't see what was happening inside? We'll build a FastMCP tool that processes numerical data while sending real-time debug, info, warning, and error messages directly to the client, so you can track execution step by step, even in production. You'll see how structured logging keeps users informed and helps catch issues before they become failures. From FastMCP, import FastMCP. Context. MCP equals FastMCP. Logging demo. At MCP, tool. Async def analyze data. List float, CTX, context, dict. Analyze numerical data with comprehensive logging. Await CTX, debug, starting analysis of numerical data. Await CTX, info, F analyzing len data points. Try, if not data. Await CTX, warning, empty data list provided. Return, error, empty data list. Result equals some data/len data. Await CTX, info, F analysis complete average. Result. Return, average, result count, len data. Accept exception as E. Await CTX, error F analysis failed. SDR E. Raise. This demonstrates the client-aware logging pattern, where server-side operations emit structured log messages directly to connected clients. Unlike traditional server logging that writes to files or consoles, this approach treats logs as part of the client-server communication protocol, enabling real-time visibility into backend execution. The distinctive aspect is its dual-purpose nature. Logs serve both debugging needs and client-facing progress reporting through the same channel. The pattern works by embedding logging capabilities within the execution context, creating a unified communication pipeline. Each log level, debug, info, warning, error, becomes a discrete message type in the protocol, while the context object abstracts transport details. This design maintains separation of concerns. Your business logic focuses on processing, while the framework handles message routing, serialization, and delivery to clients. This approach solves the observability gap in distributed systems where clients need awareness of server-side operations. It's particularly valuable for long-running processes, debugging complex workflows, or when clients must react to intermediate states. The trade-off is increased network traffic for verbose logging, but the benefit is eliminating the need for separate progress APIs or custom status polling mechanisms. Let's break it down. From FastMCP, import FastMCP. Context. This imports FastMCP, the core class for creating AI callable tools, and context for structured logging and progress reporting. These are the foundational components for building observable, AI-integrated functions. MCP equals FastMCP. Logging demo. This initializes the FastMCP instance named Logging Demo, creating the core bridge between your Python functions and AI models. All tools must be registered through this instance, which handles routing, validation, and execution. The name identifies this toolset in logs and error reporting. At MCP, tool. Async def analyze data, list float, CTX, context, dict. Analyze numerical data with comprehensive logging. Await CTX, debug, starting analysis of numerical data. Await CTX, info, F analyzing len data points. This defines an AI callable tool using FastMCP's decorator pattern. The CTX parameter follows FastMCP's standard logging interface, providing structured debug and info channels that integrate with the AI's execution trace. The initial log messages establish an execution trail. Debug marks the start, while info captures the input size. This pattern ensures observability for both developers and the AI system monitoring the tool's execution.
Try. If not data.
This is defensive programming against empty inputs. The check prevents division by 0 errors later in the calculation, while the warning provides visibility into the data quality issue. FastMCP tools should always validate inputs before processing.
Result equals sum data / len data. Await CTX. Info F analysis complete average. Result. Return average. Result count len data.
This calculates the arithmetic mean and returns structured results. The CTX info log provides visibility into the computation outcome, while the dictionary return format ensures consistent output for AI consumption. This pattern of logging plus structured return is standard for FastMCP tools.
Accept exception as E. Await CTX. Error F analysis failed. SDR E. Raise.
This is the error handling pattern for FastMCP tools. It logs the exception via the context parameter, ensuring the failure is visible in monitoring systems, then re-raises the exception to prevent silent failures. The pattern maintains both observability and proper error propagation. Structured logging pattern. FastMCP's context object transforms simple logging into structured data streams, where every debug message, warning, or error becomes both a human-readable event and machine-queryable metadata. The extra parameter in logging methods silently enables rich analytics without changing the core logging syntax. This pattern bridges the gap between debugging and production observability using the same code paths.
The log message that carries no data reveals everything.